Welcome to the first video of my new video series, Nim SDL2 Game Development for Beginners, Setup and Your First Moving Image. In this video, I will tell you about SDL2, what it is, what it's used for, installing Nim's SDL2 wrapper, and teach you how to open a window using SDL, draw an image onto that window, and move it using the arrow keys. There is quite a bit of boilerplate necessary code to be written for any SDL application, and there will be several new things of the Nim language that I have not yet taught you in this video, which is why this video will be quite a bit long, but everything will be explained over the course of this video. In this video, I will tell you about SDL2, what it is, what it's used for, installing SDL2 Nim's SDL2 wrapper. SDL, Simple Direct Media Layer, is a C programming language's library, not a game engine. It is designed to provide low-level access to video, audio, input devices, threads, shared object loading, networking, and timers. It is used for making 2D games directly or to be used as the backbone of an engine on top of it, like Valve's Source Engine, which powers all of their games, some of which are the Half-Life franchise, Portal franchise, Team Fortress, etc. It is also often used for 3D games using OpenGL, as OpenGL only does 3D rendering. It can be used for other non-game related multimedia software. SDL does not have physics, so a game using just SDL cannot have physics. For that, you would have to use a library like Box2D. Because SDL is written in C, it is cross-platform, and it officially supports Windows, Mac OS X, Linux, iOS, and Android. Now I will show you how to set up, install SDL's wrapper called SDL2 Nim on your computer. This wrapper simply makes it easier to use SDL with Nim. This wrapper also comes along with all the required files we will need in this series. First, we will install SDL2 Nim on our computer using Nimble, Nim's official package manager, which comes with Nim. In order to use it, we will first have to open up a command prompt, which is short for CMD. So let's do that. Open up your Windows search field and type CMD or command prompt. I will type CMD on mine. Click on this one with the black console icon. Once inside the console, in order to use Nimble, we have to type Nimble and then the arguments, commands we want it to run. If we simply type it without parameters, just Nimble, it will display us a list of all the available commands. So let's try that out. Nimble and enter. Here we go, all the commands it has and their arguments, parameters. Now we will install our required wrapper by typing Nimble install SDL2 _ Nim and press enter. Now it's going to download it. Will take a couple seconds. SDL2 Nim wrapper already exists on my computer, so I'm just going to override it. Yes. And once you get the green success, it means it's successfully installed. We can now close this window. Now the wrapper is installed on our computer, but we are also going to clone the repository of this wrapper in order to get the image we will be using for this video and to provide you with lots of examples of various SDL functionalities to use outside of this video. To do this, type SDL2 _ Nim into Google inside your browser, SDL2 Nim, and click on the one that says Vladar 4 SDL2 _ Nim, and then click on this green button over here that says code, which will drop this down. Then click on download zip. Now save it on your computer. Once it finishes downloading, open the zip and extract it somewhere on your computer. I will just pop it onto my desktop. Now I will go to my desktop, SDL2 Nim Master, open it up, examples folder. Here are all the examples I told you about earlier, and here are all the assets, resources they use. The image folder, which we're going to use as well. So I'm going to copy this and put it in the project folder for this video over here. Now we need to go and get the rest of the required SDL DLLs. I have provided my own links in the video's description, but they're also in the clone repository of the wrapper inside the links file. Let me show you that. SDL2 Nim master folder. Here we go, links.md. And then if you're using Notepad++, double clicking one of these links will open it up, but this closing bracket will also appear which will give you the wrong URL, like this. So just remove this bracket and it will work. Here we go. Okay, let's get the main SDL DLL that we require on this link. Here we go. For Windows, you have two choices depending on the bitrate of your operating system. Mine is 64-bit, so I will take this link, save it on your computer. Now let's get the rest of the DLLs. So this URL from the description, and over here under runtime binaries, Windows, again the bitrate here of your operating system. For me, 64-bit, so this one. Save it again. Now let's extract the main SDL DLL from the first link into a projects folder. So this second one, and let me find my location. There we go. And now for the second one, extract zlib1.dll, SDL2 image, and libpng16 and their corresponding license files. Okay, so the first one for me, and I will select now the required files and the licenses, and Control C, copy this and paste into the folder. First, we will begin by importing the DLLs, dynamic linked libraries, that we have downloaded and put into our projects folder. Let's type import SDL2/SDL to import the first most important SDL library, the main one, then comma SDL2/SDL image as img. This SDL image is a extension library for SDL to provide image manipulation and drawing, and we rename it as img for easier usage. Now we make our constants for our program's window and set the parameters on how our renderer object will render our image. A constant is a variable that must be initialized at compile time, and it cannot change, is immutable. Here we make a variable constant renderer flags, which will contain the parameters for our renderer. The first, renderer accelerated, is to enable hardware acceleration, and the second one is for vertical synchronization, which synchronizes the present current frame with the refresh rate of our monitor. Renderer is simply an object SDL uses for drawing our stuff. This OR over here acts as an AND in this case, because we're doing a bitwise operation. These two are bitwise flags, and this is more optimal. So this line of code simply enables hardware acceleration and vertical synchronization. Hardware acceleration simply means using your GPU graphics card to assist your CPU processor in rendering drawing things onto the screen. Now to explain this OR keyword in this context a little more in depth. OR keyword in Nim is used in logical operations with multiple conditions, like an if statement. OR keyword, when used with two logical conditions, means that if either of the two conditions is true, execute the if statement. But OR keyword, when used with enumerators and sets in Nim, or when interfacing with C programming languages libraries, which SDL2 is written in, acts as an AND keyword instead. Both SDL renderer accelerator and SDL renderer present vsync are integers, and the default integer in Nim is integer 64, made out of 8 bytes, and each byte is made out of 8 bits, ones and zeros of the binary system every computer uses in the lowest level. And when doing bitwise operations, OR is to set a flag to true, a 0 to 1. Computer circuitry is made of billions of transistors. They are logical gates of ones and zeros. 0 means that the logical gate has no electrical charge, while a 1 that it has an electrical charge. The base data type for data in computers is called a byte, and a single byte has 8 bits, 8 logical gates of zeros and ones. In the lowest level of computers, the hardware level, computers use the binary system, and every programming language in the end translates to it. The reason for bitwise operations, setting flags, is that it's far more efficient and faster to set a single flag of our SDL renderer's flags parameters to true than to add the two integers together normally. A little more on the binary system. Binary system works with bytes. The only numbers it can have is 0 and 1. It works from the right to the left, and so when working with a single byte, you will have 8 bits and start at the 8th bit, then work your way to the left. In order to increase the value, you must change a bit from a 0 to a 1. That adds 1, but if the bit is already a 1, say the first one, 8 1, Then you check the next bit, the 7th, if it's a 0. If it is a 0, then you set the 8th bit to a 0, and whenever you change a bit from a 1 to a 0 when adding, you must then carry over that 1 to the first non-1 bit. This all reverses when subtracting. You start at the first bit from the left to the right and work your way to the right, reversing what you did in addition. Let's create a new file called binarysystem.nim. Let's demonstrate the addition by starting with an empty byte, then keep adding a decimal value of 1 to it till we reach 10. Decimal value is the normal numbers we use from the decimal system. We use it to read what value a byte or more holds. For example, whenever we used an integer, int, in our programs, we made a new variable that could only hold whole numbers, no decimals, of 64 bits in size. The reason it is 64 bits is because int is an alias for int64, because almost every computer on the planet today uses a 64-bit operating system, and these operating systems work with many 64-bit chunks at a time. So whenever we made an integer variable, the computer then reads it 64 bits at a time. It does it at an incredible speed though. Now let's demonstrate this, but let's only use 4 bits to make this easier to demonstrate. Okay, so now we have 4 empty bits over here. Their value is 0. Now let's add 1. So because the first one is empty, we can add it straight to the first one. So 1, and the value of this is 1. Now let's add 1 again. Now because the first bit is already a 1, we make it a 0 and carry over this 1 to the next bit over here. So 1 0. This is value of 2. Now for another addition, because the first bit is a 0, we can set it to 1. So 0 0 1 1. This is value of 3. Now for the next addition, because both of our first bits are a 1 already, and then the third bit is a 0, we can set these first 2 bits of 1 to 0 and carry over the 1 to the third bit. Let me write this down. 0 1 0 0. This is value of 4. Now we have 2 zeros behind the 1, so we can repeat the same procedure as we did above. So we copy what we had above, and then 0 1. This is 5, and then another addition. Now because the first bit is a 1, we set it to 0 and carry over the 1 to the next bit. So 1 0. This is value of 6. Now to increase the decimal value of 6 to 7, we have the first bit at 0, so we can increase this one. So 0 1 1 1. This is value of 7. And now for value of 8, since only the last bit is a 0 and the first 3 are a 1, we set them to 0 and carry over the 1 to the fourth bit like this. 1 0 0 0. This is value of 8. Now for the last 2, 9 and 10, we do the same as above. So we set the first 0 to 1, and this is 9. And then because the next bit is a 0, we can change that to a 1 and set the first one to a 0 by carrying over that 1, and thus this is value of 10. Now let's do the reverse and do the subtraction. For this you must reverse your thought process. You now instead look for the first one from the left to the right, and then if all the bits are 0 to the right of it, you can change it to a 0 and carry the 1 to all the bits to its right. But if it does have 1s to the right of it, you move to the rightmost one. So in case of 0 1 1 1, you change the last bit, the fourth one, to a 0. But since it's the last number, you don't and can't carry it over. The bit pattern is now 0 1 1 0. Now you can carry the 1 over, so you carry the third bit 1 bit to the right, or in other words, change the 1 to a 0 and the bit on the right of it to a 1. Now I will hide this so we don't cheat, and we start with the highest one, so 1 0 1 0, which is value of 10. So here we have a 1, and then we look to the right of it, we have a 0, and here's the last 1, so we can change this one. So we repeat the above first 2 bits, and then change this 1 to a 0 and carry over the 1 to the right. So this is value of 9. Now the last 1 is the first bit, so we change this one to a 0, and since it's the last one, we don't carry the 1 anywhere. So 1 0 0 0. This is value of 8. So now we are left with a bit pattern which only has a single 1. This is the rightmost one. So we have to change this one and carry over this 1 to all the zeros on its right. So this 1 becomes 0 and we carry the 1. So 1, 1, 1. And this is value of 7. Now the rightmost one is the last one or the first one. So we change that one and repeat the first two. So 0, 1, 1, 0. This is value of 6. Then the rightmost one is this one. So we change this one and carry over the 1 to the right. So 0, 1, 0, 1. This is value of 5. Now the rightmost one is this one. So we change this one. And since it's the last one, we don't carry over. So 0, 1, 0, 0. This is the value of 4. Now the rightmost one is the second one here. So we change this one to a 0 and carry over the ones to its right. So 0. This one becomes a 0 and the next two ones. So this is value of 3. Now the rightmost one is the last one. So we change that one to a 0. So 1, 0. This is value of 2. And then the rightmost one is the second bit here. We change it to a 0 and carry over the 1. And here we have a 1. And the last step is of course zeros. And now we check if we did any mistakes. And we start at 10. So 10 is the same. 9 the same. 8 the same. 7 the same. 6 the same. 5 the same. 4 the same. 3, 2, and of course 1. I must mention that there is a module called BitOps, specifically made for bitwise operations. There you can find many more procedures, etc. to work with bits. Now I will demonstrate bitwise operations in code. We will start with the OR operator we saw earlier to set the renderer's flags parameters. Here I have created 3 variables. The first one flag holder to represent renderer flags, and then the next two as the flags. Now we are going to set the flag holder's flags as in the first and the fourth bit, which are these two in these flags, which will result in the last 4 bits being 1, 0, 0, 1. So let's do that. So flag holder is flag 1 and then OR keyword like before, and flag 2. Now this will put them together. Now to display this, we will do that with an echo flag holder and then to bin to be able to see the bits, and the parameter is a number of how many bits you want to see, so 4. And now this procedure is located in the strutils module, so we have to import that as well. So let's import it here, import strutils, and now let's run this. Here we go, 1, 0, 0, 1. We set the flags. Now I will show you how to remove a flag. So in order to remove a flag, we must use the AND keyword and inverse the flag we're ANDing to the flag holder. Here I have put an empty line to make this more readable. And now let's demonstrate this. So flag holder and then flag holder again because we're changing it. And then to remove a flag, we do and then to inverse the bit pattern, which we have to if we want to remove a bit. So not keyword and then the flag we want to remove. So flag 2. And now let's display this with an echo flag holder and to bin 4. And now let's run this. Here we go. We removed the 4th bit, or in our words, the first one, as in set it to 0. Now to clear the first flag, since we already did the second one, let's do the first one. Let's copy paste this and flag 1 and then echo and run this, F6. And here we go. All the bits are 0, both flags are cleared. Now we can also check if the flags are set, but before we can do that, we have to set the flags again. So let me copy paste this. So setting the both of the flags. Okay, to do this, we need an if statement and parentheses. So flag holder, and then like I have written above, if you use an AND keyword without the not keyword after it, it is used for checking bits. So flag holder and check flag 1 and then OR to combine them together to check for both flags. So flag 2, and then outside of this, larger than 0, as in if the bits are larger than 0, that means they are a 1 and thus they are set. And now use an echo to display the result. Both flags are set. And now let's run this, F6, and here we go. Both flags are set. Now you can also toggle invert a flag state value with the XOR keyword. Now let's first check what the bit pattern is. So flag holder to bin to show that. F6, here we go, it's 1001 as in both flags are set. Now let's toggle invert both flags, flag 1 and flag 2. So flag holder is flag holder because we're changing it, and then XOR, and then in parentheses because we want to toggle both the flags, so flag 1 or flag 2. And now we display this, copy paste this, and run F6. Here we go. Both flags are now 0. The whole pattern is 0. Now let's repeat this toggle if it actually keeps toggling, works. So flag holder, we just copy paste this and run. Here we go. It did. First we had 1001, then we toggled, and thusly the first one, flag 2, and then flag 1, the last bit, inverted to 0, and then we inverted them again, back to 1s. So 1001. Now we are done with the binary system bitwise operations, so let's head back to the main program of this video. Now we're going to create objects we need for our program. Here we create a reference object to the app object. A reference is, in other words, a pointer, and it points to the memory location of the data instead of actually holding the data itself, which is very useful for when you want many objects or have many procedures, etc., accessing the same object variable, whatever. And the reason it is useful is because if you had a normal plain object, you would be copying that object every time. While using a reference, you will instead access that data directly, which also means that if you modify the referenced object's data, and any and all code using that reference object will have their data changed, as they are all accessing the same data. So here we created a reference object to the app obj because we do not want to have multiple SDL applications with its own window and renderer running. We only want one. Think how games only always have a single main window. Here we create our image object that we will use for our image and a reference to it. Why do we need a reference pointer to it? Well, because in future videos, say you wanted to have walls around your level, so your player cannot leave. For that purpose, creating a new full value object would be a waste of your computer's memory, since you will most probably use the same image texture sprite for all of them. Now that we have our constants and objects with pointers made, we're going to make procedures to make a new empty image object, free an image object's texture, as in the image which when loaded into computer's memory, RAM, is called a texture. We will also need a procedure to load the image from a file into memory. First, we create our procedure to make a new image, which simply makes a new object and initializes it with empty values. We set texture to nil because a pointer cannot have a 0. You have to give it a nil for an empty value instead. Next, we create a free procedure, which simply takes an image object and then destroys its texture, frees it from the memory, in order to prevent memory leaks and optimize. For example, if the application game were to become big, it would run well. Here I made a procedure called load in order to load an image from a file. The first argument is obj as image. We must provide it with an image object. Then the second one is renderer. Renderer is responsible for all loading of textures, unloading, freeing, drawing onto the screen, etc. So we supply this one from the pre-made constant above, and then the file we want to load the image from. In this first line of code, we set the implicitly returned variable result to true, which will always be true unless it fails to load an image, which then it will be false. In this next line of code, we load the texture from a file into our object's texture field by using the renderer to load the texture from the parameter we supplied. Next, we check the object's texture, which we loaded, if it's equal to nil. If it's nil, then we don't have an image, which is an error, and then we log that by using the SDL log critical procedure and give it the category of the error and the error itself, and then return false, which terminates this procedure, which also gives information back to our main loop, which we're going to use below, that it failed to load an image, and using that information we will close the application. Next, we create two variables, w and h, short for width and height of our image, of type sint, a special integer for interfacing with the C programming language. Next, we call the query texture procedure on our texture in order to retrieve its width and height by using pointers and store the texture's attributes into our w and h variables. And we use pointers because, again, we do not want a copy of its attributes. This way it's faster. And addr retrieves the location, the pointer, to the w variable's location. And then if the result is false, that we cannot get texture's attributes, we log the error again by giving the log the category of the error and the error itself, and then we destroy this texture that we couldn't get its attributes, and we return false, terminating this procedure and giving the information back to the main loop in order to terminate the application because something went wrong. And then, once we have successfully retrieved the texture's attributes, we put them into our objects w and h fields. This completes this procedure load, and we go to the next one we're going to require. This next procedure will be called render, and it will render the texture onto the screen. These coordinates are relative to the window that we're going to create later. Next, we create an empty rectangle shape of width and height equal to those of our image's texture to be used as a drawing surface, which will be then drawn onto our application's program's window. It can also be used to only draw a portion of the texture. Here we supply our SDL's renderer object with a copy of our texture by using the render copy procedure, which can render draw only a portion of the texture if so desired, but we gave it the memory address pointer of our newly created above rectangle drawing surface, which is this exact same size as the texture itself, so it will draw render the entire texture. And we do all this in an if statement in order to check if it actually renders successfully. If it doesn't, it fails, and we give that information back to the main loop to terminate the application. Now we have all the procedures necessary for our image drawing, freeing, etc. So we proceed with the required boilerplate code of SDL. So we're going to make a procedure called init that will initialize everything SDL requires, and we will give it an argument of app as in the application, so we can manipulate that and destroy it in the end. First, the most important thing to do when initializing SDL is to initialize its video and timer. This OR is a bitwise OR. So these are the flags and we put them together. So we initialize the video and the timer. The timer is required in order to know when to draw frames, especially if you want to limit how many frames per second, FPS, the application program will draw per second. Again, all of this is done in an if statement in order to ensure that SDL will initialize correctly and log the errors so that we know if something goes wrong, what gets wrong so that we can fix it. And then if it goes wrong, of course, terminate this initialization procedure. And later we are going to use another procedure which will then clean up after ourselves. Next, we initialize load SDL image DLL shared libraries, PNG format image support. SDL2 is spread across multiple DLLs, dynamic link libraries. .png format allows for background transparency, which allows for drawing images, textures without a background. Otherwise, if you say you used a .jpg, .jpeg format, you would draw a visible rectangle of some color, which is okay if the image has no background, but a problem if you want to draw anything but a rectangle. Next, we create our window in windowed mode, which is the default setting. You can see the borders. The vast majority of games launch in full screen mode, and we give it our constants we created at the start. Next, we add some code for error checking this window if it was created successfully and log these errors. The parameters for this create renderer procedure are, as you can see. Now again, we also have to provide error checking for this newly created renderer as well, because everything must work properly. So this is the code. If this renderer is equal to nil, then log the error again and terminate. Next, we're going to set the drawing color, which will be used for the background of our window. The parameters are, the first one being the renderer, which we apply this to. Then first we have the red color, then the blue, the green, and the alpha value. All of these values are in the hexadecimal number system, and alpha attribute parameter of an image means the image's opacity. Value 0x00 would be 0, which is completely transparent, invisible, and the one we have here, 0xff, which is 255 in the decimal system, is completely visible, the maximum number. The values of red, green, and blue are of the value of 0 in the decimal system, and all of 3 of them being 0 means the black color. If all these 3 values would be 0xff, as in 255, the max value in decimal system, this would represent the white color. Once again, all of this is done in an if statement for error checking. And now if everything went according to plan, that everything worked successfully, then we're going to log to SDL that we initialized the SDL successfully and return true. So this procedure now is finished, and now we're going to create the exit procedure to clean up after ourselves. So first we destroy the renderer, then the window, then quit the image library extension, and then we log that the shutdown is completed, and then quit SDL itself. Now we're going to make a procedure to handle our arrow key button presses, with which we're going to control our image around the window. These button presses are called events, as something happened. This procedure will detect these keys being pressed as events, figure out what category they are. Buttons can be pressed, released, and held. This procedure will also terminate our program if we will press the escape button or click the X button of the window we will create in the init procedure before this procedure will be used. And lastly, this procedure will then return a sequence of processed key presses with category, etc. determined. This procedure will be called events. For the first line of code, we're going to set the implicitly returned result variable to false, because unless we will press the escape or the X button, this procedure will return a sequence of processed keys. Next, we're going to create a new variable and call it E as a SDL event data type. Next, we're going to check with an if statement this pressed variable containing the sequence of SDL key code, its length. If it's more than 0, then we have pressed a key, and then if we have, clear it to an empty sequence, because we don't want to use any events from before, because this events procedure will be called basically once per frame. So if we had 60 frames per second, then it would happen 60 times a second. The reason we use the var keyword here for our pressed argument is because we do not want a copy of the sequence of the key codes. We want full access to it and be able to change it. Next, we process the keys events, if there are any, by using a while loop to continuously do this until there are none left. And we use the variable E of type event that we used before, and we have to check if it's actually a valid location, and then if it is, this poll event will store an event into it, and then we're going to determine the kind of this event. First, if the event kind is equal to SDL.quit, which means the X button of the window, then we're going to terminate the program. Next, we check the event kind, if it's SDL key down, as in button pressed down, and if it is, then we add it to this sequence by the add procedure. And then if this doesn't happen, we don't terminate the program by clicking the Windows X button. We check for any keys being pressed down, and then we add them to the sequence pressed by the add procedure. The argument we give it first, e.key, is the raw key, and then we call the key sim on it, a lookup table, and then .sim to get the processed key. And then in the same elif statement branch, we check if the one of the keys being pressed down is kescape, and if it is being pressed, then we terminate the program. All the boilerplate code is now done, so we proceed to the main program. Now we need to make some important variables. First, we're going to make app, which will be the app object, and we're gonna initialize its field as empty pointers, because again, we're working with pointers now. And then we need a done variable set to false, which is the main loop exit condition. And the last variable we need is the pressed sequence, which will hold the keys. And now we are going to initialize our application, and we're going to use an if statement so that if something goes wrong, we terminate it. So we're going to use an if statement and then init procedure that we made. Now, the first thing we're going to do is load the image. and give it all the parameters it requires. First, image as a new image, the proc we made earlier, to initialize an empty image object. Now we need some variables to hold x and y positions of our image. So image pos as a tuple, and we're going to use a tuple because they're better suited for just two fields than objects, and use float data type for its x and y fields because we require precision. Integers won't cut it because you may try to do it with integers, but you're going to get some very unnatural movement. Then next we need the speed at which our image will be moving on our screen when we're going to be pressing the arrow keys. So image speed, and we give it the value 200, which means 200 pixels per second. It may sound much, but you got a big screen. Now we're going to load the texture for our image object we made over here. So first we're going to exit the var section, and here's the code. So if not image loaded, so if image won't load, and this is the image we're loading with the app renderer. So if it can't load, we're going to log a critical error with the category and the error. Otherwise, it's going to load the image and then done to true, so no error. We can proceed. Now we're going to set our image's position. So with this code, image pos.x to screen width divided by 2, and the y as well. This will give us the center of the window we're going to create. This next part is required for any game whatsoever. I will try to explain it, but if you won't understand me, don't worry about it. Just make sure that you have these variables where I have them, because without them we cannot work with SDL. So what we're going to do is make a delta, ticks, and frec, short for frequency variables, which we will use in order to synchronize rendering of our scene, our image, and the background in black with the frame rate, which is synchronized with the frame rate of your monitor by the vsync vertical synchronization parameter we set to our renderer as a flag parameter at the start. Now here I have made a variable called delta, which is just a float, but this variable will hold the time pass since last frame in seconds. Now the second variable I mentioned, tick, as a uint64, which means unsigned integer of 64 bits in size. Unsigned means that once you reach the limit of its size in either direction, negative or positive, it will loop around to the other end. Here we need it, but in general avoid using unsigned data types unless you know what you're doing, as you might get unwanted values and with that behavior. Now the last variable I mentioned, frequency, is SDL get performance frequency. Like I have written in the comment, gets us the high performance counter frequency, or in other words, the speed our processor is running at. Now, before we capture the high performance counter again, we're going to echo the message to use the arrow keys to move the image. Now we will begin with the rendering, the start of it. Now we need to capture the high performance counter current value. So this is the first time we are capturing this, giving it to the ticks variable. This process will be repeated at the end of the main game loop, which we're about to start. Now we're going to create the main loop of our program. Now this loop is required, otherwise everything will execute just once and the program will terminate as quickly as it started. Now for the reason for the not keyword here is if we are not done, it means that we had an error and we will terminate the program. Now for the first part of our main loop, we're going to try to set the renderer's draw color to black. This procedure returns true or false, but if it doesn't succeed or it does, we don't care about the results, so we're going to discard it. Now the reason we don't care about the return value of the set renderer draw color is because in the next bit of code we're going to clear the screen by renderer clear procedure, which by default clears with the black color, so this is just precautionary. Here in this next bit, we render draw our image. Earlier we set our images x and y to the center of the screen. Here we use those coordinates and call .int on them in order to convert them to the integer type, because the renderer proc from the SDL library requires integers as coordinates, and then since the original actual position where the image will be drawn is the top left point of the image, all images on your computer are stored as rectangles, and so that top left position is what will be the starting point of the image, which will make the image be drawn a bit to the right and down. So we fix that by subtracting half of the image's height and width from the corresponding coordinates to truly center the image. Here we also use the discard keyword because even if rendering the image fails once or twice or more, it doesn't matter because the frame rate of your monitor is quite high, so even if one frame doesn't work, it doesn't matter, as you will most probably not even see the failure. And now we update the renderer with all the changes we have made, which includes putting our image into the renderer to draw. This will now fill the window with black color as background and our image to the coordinate we set it to. Now let's run this and see what we have made. So F6, here we go. We have opened a SDL window and drawn an image onto it, but we don't have any keyboard input, so we can't even click the X button properly, because if we do, Windows will have to close this for us. Now, once all the rendering is done, we will process our key presses. And we do this with this line of code, setting done to events and the argument as the pressed sequence. And then if done is set to false through the events procedure, then we have pressed X or escape button, so it exits the main loop, and with that, the whole program. And now for the most difficult part of this video, we're going to calculate the frame duration, the delta variable we made earlier. Now to explain the delta, the duration of a frame when synchronizing to 60 FPS is half of the duration than when synchronizing to 120 FPS. So earlier above, we retrieved the high performance counter's value before we rendered our image, and now we capture it again after rendering our image, and subtract the previous value from the current one, convert it to float for usage with our image's speed, which is a float, and then we divide it with the frequency speed of the high performance timer, which gets us the duration of the frame. Note that if we had more images, objects, etc. to render, we would do it exactly like we did now. First, the high performance frequency, and then the current high performance counter value, and then do all the rendering, then get the high performance counter value again, and lastly calculate the frame duration, which we will require for moving our image at the frame rate we want. In this case, the frame rate our monitor is running at, since we got VSync on. So this line of code gets us the frame duration, and we do this by taking the time at the start of rendering minus the time at the end into float and divide it by the speed we're running at. Now we're going to capture the high performance counter value again, because this is the main loop and we first captured the counter just before the loop started, so we have to do it again, otherwise we have only synchronized the very first frame. Next, we're going to get a snapshot of the current state of the keyboard with this line of code. Now here, if the parameter is not nil, then it will return the length of the returned array of key states. But if we use the value of nil as the parameter, it will return not the length of the array of the key states, but the actual array of the key state. Here we check for all 4 arrow keys if they are active, and if they are, we then change the position of our image, make it move. We also multiply the speed of our image with the delta, in order to synchronize the speed with the frame rate of our monitor's refresh rate, which is why we have enabled VSync, vertical synchronization, renderer flag. Otherwise, we would have to synchronize differently, like setting a constant FPS of like 60 FPS. If we don't synchronize the speed of our image with the frame rate, then the image would move relative to the speed of your processor. The speed of your processor is vastly too fast to be used in games. You can try removing the multiplication with the delta below and observe how your image will fly off the screen in an instant the moment you press any of the arrow keys. And now all we have to do left is the cleanup part. So here we're going to free our image once the game loop is done to prevent memory leaks, etc. And then outside of the game loop, we run the exit procedure in order to clean up after ourselves once we press the X button or the escape button. Now let's run this. F6. Here we go, image. And now let's move it with arrow keys. Here we go. It moves with arrow keys. Okay, that's it for this video. Thanks for watching. Like and subscribe if you liked it. You can also support me on Patreon. If you had any problems with any part of the video, let me know in the comment section. The code for this video is in the link in the description, as well as the link to this video's documentation script as a form of an offline tutorial. Have fun!